Okay, we've touched on matrix inverses in previous videos. It's time to dig in now and figure out how to actually calculate these things. To start, let's make sure we know what inverses are. Let's start with a number, scalar. If I say 4 times 4 to the minus 1, that's the same as 4 over 4, and that equals 1, right? We know that. Now, for notational reasons, we don't divide matrices, we multiply by the inverse. So you'll never see somebody divide one matrix by another one. It works in scalars, not matrices. Well, what would that look like if we were dealing with matrices instead of numbers? Well, let's just go over here. If I have two matrices, A and B, if I multiply those, and what I get is the identity matrix, then A and B are inverses of one another. What's the identity matrix? Okay, let's call it I2 for a 2 by 2 matrix, is 1, 0, 0, 1. I3, or 3 by 3 matrix, is 1, 0, 0. Okay, identity matrix just has ones along the diagonals and zeros everywhere else. This is the matrix equivalent of 1. If you multiply a matrix by its inverse, you get this, just in the same way that if you divide two numbers, you get a 1. This is the matrix version of 1. So if I get this, then, let's go down here, A inverse equals B, or B inverse equals A. That's another way to write this. One of those is the inverse of the other one. This is one of those few times when commutation works with matrices. If A and B are inverses of each other, it doesn't matter which order they appear in, you're still going to get I. So if you multiply a matrix by its inverse, you get I, in the same sense that if you divide a number by itself, you get 1. That's what's going on here. So that's the definition of an inverse. So how do you make one? Well, you might be wondering whether there's such a thing as an analytical inverse for a matrix. There is, but you're not going to like it. So here's what it looks like. So analytically, if you want to just figure one out directly, here's what it looks like. A inverse, and make sure I get this right, 1 over that. There, that's an analytical inverse. Now, this looks maybe not as bad as it is. This thing is called a cofactor, and that thing right, that T right there is a transform. So what would this look like? Let's try this with a 2 by 2 matrix. Let's say that A equals the same one we've been messing with. I know you've seen this many times before, but it's as good as anything. So what's a cofactor matrix? Well, for a 2 by 2 matrix, I'm going to reverse the elements along the diagonal and change the sign of the two elements off diagonal. So I get -2 and -3. So what's the transverse of the cofactor? Well, it's the transverse of that. So I get 4, 1, -3, -2. I'll get my head out of your way here in a second so you can see that. So let's go ahead and run this. We know from before that the determinant of A was -2. So we think that the inverse of A is 1 over -2 times this. Okay, so it's 4. Now, if you work all this out, what you get is -2, 1. I mean, I'm looking at my cheat sheet here to make sure I get this right. 1.5 and 0.5. Did I get that right? I did, -0.5. There we go. Is that the inverse of the A matrix? Yes, that is. That's actually it. We got it right. All right. So this does work. I mean, for sure this works, but it gets very, very cumbersome as matrices get bigger. Well, what do I mean by bigger? Well, by hand, this would be hard to do for certainly 3 by 3, definitely 4 by 4. After that, you're out. You don't want to do this by hand. Analytically, I mean, numerically, you can ask MATLAB to figure these things out, but it's not very efficient. There are other ways to do this that are much more numerically tractable. So this does work, but it doesn't get used very often. A much better way to do this is using row operations and the idea of an augmented matrix. So here's what I'm going to do. Let me clean out the board here, and I'm going to do the same problem now in a more scalable, more efficient way, okay? Okay, a more scalable way to do this is using Gauss-Jordan elimination. And what we're going to do is operate on not just the A matrix, but an augmented matrix that has the A matrix and then next to it the identity matrix of the same size. So here's what this would look like. I'm going to call little a the augmented matrix. 1, 2, 3, 4. Now we've seen that before. And there's the identity matrix. So that half is the original A matrix, and this half over here is the identity matrix. And so what we've done, if you want to look at it this way, our augmented matrix looks like that. It's our original capital A matrix with an identity matrix appended to the back of it. It's called an augmented matrix. Okay, so what we're going to do now is pretty straightforward. We're going to perform row operations until we have the identity matrix on the left-hand side rather than on the right-hand side. In fact, I'll put that there for right now. We'll eliminate the dotted line here in a minute. But we're going to do row operations until we have the identity matrix on the left-hand side. The matrix on the right-hand side will be the inverse. And the reason this works is that because these successive row operations are mathematically equivalent to multiplying this matrix by its inverse. So let's go ahead and do this. I think the matrix fairy just visited. Cool. So let's walk through this step by step. So there's the augmented matrix. This is labeled R1 and R2 for row 1 and row 2. So we're going to just repeat row 1 there. So copy the back over without changing it. Row 2 is row 2 divided by 3. So now I've got a 1 in both in the columns there, first column there. And then I'm subtracting row 1 from row 2 to make a 0 there. And you can see that this side is starting to look like the identity matrix. Well, let's go a step further. Okay, we'll just recopy row 1 again. And row 2 equals row 2 times minus 3 over 2 to turn that into a 1. And boy, we're getting close now. So the last thing to do is subtract 2 times this row from that row. I could break this down into more steps, but this is just a little quicker. And there it is. There's your identity matrix right there. That's the one we're looking for. And that means what's over here is the inverse of A. Well, is it? Well, yeah, that's what we found before. So that's pretty good. And this is called reduced row echelon form. Now, as I mentioned before, when you study linear algebra, it seems like about half of what you're doing is learning terminology, and this is probably one of those times. So this is called reduced row echelon form, and of course there's a command like that does this in MATLAB. So let's go ahead and repeat this same thing, but let's do it in MATLAB.